Hello, this is Jack Jackson. We're back again with another example of looking at limits formally, see if we can try to get an even better understanding of this idea of this delta and epsilon thing. So in this example, we're going to look at a quadratic function. So we see the 3x squared plus 2x minus 8. Now intuitively, we kind of know that this should be, just by graphing a lot of quadratics in the past, we know that it's all one connected piece. So it should be a continuous function. We should be able to find the limit here by just plugging in 1 for x and evaluating it. And of course, when we plug in 1 here and here, we get 3 plus 2 is 5 minus 8 is negative 3. So we've seen that the limit is negative 3, and that's going to be our claim. How can we show this? Well, suppose that somebody chooses an epsilon value of 0.5, which they're basically claiming that we're off by 0.5 in our value of the limit. What would be the largest corresponding value of delta that we could use so that the conditions in the definition of limit are satisfied? So that's our task, is to come up with this delta that will work. Okay, and the largest one. Okay, so the first thing we want to notice is with an epsilon of 0.5, if we've restricted our y values into an interval from L minus epsilon to L plus epsilon. Well, in this case, L is the negative 3. Epsilon is the 0.5, so that's negative 3 minus 0.5 is negative 3.5. And on the top, we've got L plus epsilon, which is negative 3 plus 0.5, which is negative 2.5. So if we're thinking about the picture here, we're drawing horizontal lines at y equals negative 3.5 and y equals negative 2.5. And what we're going to want is pick a small enough delta so that all of the y values within the region, within this interval from c minus delta to c plus delta, all the y values will be up here. So if the x's are in this interval, the y's will be in this interval. So we want to use c minus delta to c plus delta. C is this value here, this 1, where we're approaching. So we're approaching 1, I'll plug that in for c. And so notice that this interval has 1 right in the middle. And so we want all x values in that interval to produce f of x values in this other interval. And of course that is except for x equals c, which is 1. Okay. All right. Now, so how can we start working at this? Well, let's start by thinking of it kind of graphically. Okay. So again, these y values, L minus epsilon and L plus epsilon, or in our case, negative 3.5 and negative 2.5, are y values where we can draw horizontal lines. And so let's go ahead and draw those, say, on a graphing calculator. Okay. And then let's find out where the graph of the original function crosses that. So let's put this 3x squared plus 2x minus 8 in as y1. You do it on your calculator right now. Put that in as y1. For y2, let it be negative 3.5, and y3 be negative 2.5. Or anyway, get all three of those in there, and then just graph it, and let's see what comes out. We probably want to set our window so that x equals 1 is right about in the middle of the screen. So we might go from like 0 to 2 or negative 1 to 3 or something like that to start with. And the y's, well, we need to see these two horizontal lines, but not much above and beyond and below them. So, you know, we could let y minimum be, I'll say negative 4, go a little bit lower than that, and then maybe negative 2 for y max. So with some kind of window like that, go ahead and graph them, and then use your calculator to calculate those points of intersection. Let's see if you can do that much by yourself, and then come back when you're done with that and check your answers by going forward. So press pause now, and then come back later. Press pause. Okay, well now you're back. Hopefully you've done what I asked you to do, and that is take your calculator like this, put in the original function formula for y1, put in the L minus epsilon for y2 and L plus epsilon for y3, so that goes like I've got in this screen right here. Pick some kind of window and graph it. You can see the window I chose here, and we can see, the main thing is we want to see these points of intersection. Now we want to calculate those 2 points of intersection. One easy way to do it is just do calc intersect on the graphing calculator. At least in terms of an approximate value, this will be sufficient. So if we want to find, we do calc intersect, say on this bottom one. Remember, when you do calc intersect on a TI-84, it's second and trace to get calc, and then choose the intersect. And then it's going to ask you for first curve, make sure you're on the original function. Second curve, make sure you're on this horizontal line. So make sure you're on there, hit enter. Second curve, make sure you're on the right one, hit enter. And move over about here for a guess and hit enter. And it should return what I have here. Similarly, to find the other intersection, you'll again go to second trace, which is calc, choose intersect. Identify your 2 curves. This time you're going to choose y1, but then you're going to need y3. So after you hit enter, you're going to have to do probably down arrow to get to y3, and then you can continue. Okay, and when you put your guess close to where they cross, and then you can go ahead and find this point of intersection. If you quit, at this point you hit quit and say X, and in enter it'll go give you a couple more decimal places. Okay, and you do see that it's a little bit above 1.0611, which is maybe might be important. And then you can try to change it to a fraction, but in this case it's not a nice fraction answer, so it's probably some irrational number. We'll have to figure out what it might be exactly later if we want to do that, or if we need to do that. Now that's the X value, but what could that be? Well, one of these values needs to be at a corner of our little box that we looked at before. And our little box I'm talking about is a rectangle that goes from on the left side 1 minus delta, to the right side 1 plus delta. That's C value plus and minus delta. And the bottom of the box will be this line right here at L minus epsilon, and the top will be at L plus epsilon. And you want one of these 2 points to be at the corner of the box, and the other one will either be at the corner as well, or it'll go out the side. The box, it'll be outside the box, so that the function is running out the left or right side. Okay, so that's what we want to try to find. So anyway, so that means since this is an increasing function, the one on the right where it meets, that's this one right here on the right on this picture. That's our 1.06110, and that is going to be the X value. But the X value there, if that's the corner of our box, would be 1 plus delta. I'm going to call it delta 2. So subtract 1 for both sides, and we get this delta 2 as 0.0611. Now similarly, we look at the left side, and if that's a corner, that's a left, it's going to be on the left side. So that's going to be 1 minus delta, we'll call it delta 1 this time, and there's the X value there. So subtract 1 and then divide by -1, we get this. So we have a delta 1 and a delta 2. Notice that they're both positive numbers, as they should be. But what we want is the minimum of those two is going to be the number we want. Now these are both approximated, so that means our minimum delta is the one on the right. In other words, this right corner is closer to the vertical line at x equals 1 than this left one is right here, this left intersection. So we're going to choose the one that's closest to determine our delta. So the biggest delta we can use is approximately this. Now, any smaller value of delta would work, okay, in terms of making the box so that the graph goes out both sides. So for example, and it would of course make the conditions in the definition of the limit true. So you could use, for example, 0.06, or maybe 0.05 would be smaller, or 0.01. or even anything that's smaller than what we have here. But if we want the largest delta, where delta is a 3-digit number, then we take this one and we round down. So if it was 0.0617, we would still go to 0.061 because we don't want to go up from this, because going up would allow this to go not out at the corner but out the top of the box, and that's not what we want. That will not make the inequalities work out the way we need them to. So this number must be rounded down, and if we go to 3 digits, 0.061 will work. 0.062 is not small enough. Anything smaller than 0.061 would work as well, but if we're wanting the largest delta where the conditions are satisfied, then we go to 0.061. So if you have a problem like that and you just want a decimal answer for approximation, this is basically all you have to do. What do? We graph the original function and the L plus epsilon and L minus epsilon. We find those two intersections using, we want those to be the corners. Now we used a little bit of knowledge that this is an increasing function, so we know if this one's going to be a corner, it's going to be the upper and the right. So the right side is 1 plus delta over 2. The left side is 1 minus delta 1, let's say. And this is 1 plus delta 2 for the right side. And so that allows us to solve for our delta 1 and delta 2. And then the smaller of those two is going to be our actual delta that we're going to use. So how can we sort of go back and check this, make sure we've got the right values? Well, we want to graph the original function, and we want to do it on this window. And the window we want to use is x min would be c minus delta, so that's 1 minus 0.061 or 0.939. C max, x max is c plus delta, which is 1 plus 0.061, which is 1.061. The y min is L minus epsilon, which in this case is -3 minus 0.5 or -3.5. Y max is L plus epsilon, which is -3 plus 0.5 or -2.5. And with those as the values, we set that up in the window, which is what I have here. Now what we should see is it will run out of the window at one corner, and the other side will run out on the side or possibly both corners. In this case, the corner here is closer to this vertical line in the center than this would be if it intersected the L minus epsilon out here. So that's the one we're going to use. So that goes out this corner and out this side, and then we've got the right thing that we need. Again, if we're not really that worried about which delta we choose, you know, this one's fine, but we could choose something smaller, 0.05, maybe 0.01, something convenient. Can't be 0, of course, it's got to be a positive number, but it could be anything else. As long as it's smaller than that value. If we need the largest one, we have it there. Now, we used this GeoGebra sketch before, and here you can see this quadratic. Actually, notice that the quadratic does actually touch these lines twice, once over here and once over here, but we can kind of clearly see that we're interested in near this area over here. So this part over here, the graph really doesn't have any bearing on us. So here nearby, it's strictly increasing. Overall, definitely not. It decreases and then it increases. But right in here is where we're interested. We're mainly interested in this box, and this box is the same as this window right here, which is this box. That's all you see is inside the box here. So here it is, and I've zoomed in on it right here, and once again you see it going out the corner here and out the side here, so that is an appropriate one. If we made it any bigger, then it's going to go out the top right here. Maybe at the bottom too. So that would not work. Now what is the actual value for this delta? Okay, for this largest delta. We did an approximation of it. What if we needed or wanted the exact value? And since this is a quadratic equation, we actually can solve it exactly. What we're looking at is taking where f of x, 3x squared plus 2x minus 8, that's the blue graph, touches this green line at the top, that's L plus epsilon, which was -2.5. And so we're solving that equation. Now, because it has decimals in it, and it ends in 0.5, I could multiply both sides by 2 and get rid of the decimals. And so that becomes 6x squared plus 4x minus 16 equals negative 5. And of course, notice I used the distributive property on the left-hand side of the equation. Now, if we go a little further, we can solve a quadratic equation, remember, by first setting it equal to 0. So we're going to add 5 to both sides of the equation. We get this. This one doesn't factor nicely, which is why that value before was not a nice fraction. We try to change it to a fraction with our calculator. But we can use the quadratic formula. Ax squared plus bx plus c equals 0 if and only if x equals the opposite of b over 2 times a plus or minus the square root of b squared minus 4ac over 2a. And so here's the 2 is built in. The a is the 6 here, here, and here. The b is the 4 here, here, and here. Here and here. That 4 is built in the formula. And the c shows up one time, which is right there. The rest is just some simple, some arithmetic simplifying this. So 4 squared is 16, and it's 2 negatives make a positive, so 4 times 6 times 11 plus 16 more is 280. I went ahead and took 2 times 6 and made it 2 squared times 3. 280, if you factor it down, is 2 cubed times 5 times 7, and so you see that 3 power is bigger than the 2 root, so it's basically a 3 halves power. You can make it into a mixed number, 1 1/2, so the 1 power comes outside, the 1/2 power means the power 1 stays inside. Or in other words, divide the powers by the root, 3 divided by 2. The quotient is the power outside, and the remainder is the power inside. So this is 70 when you work this out here. This 2 out front can cancel with one of these 2's here, leaves us 2 times 3 or 6 in the denominator. And the 4, 1 2 cancels with that, the other 2 cancels with the 6, leaving a 3. Of course, we still have a negative, so it's negative 1/3. Now, remember that x is 1 plus delta, and just a quick look at the graph here tells you is it's not going to be, this one over here is going to be the one with the minus, and this one over here is going to be the one with the plus. So the plus here is the one that we end up needing. And that's 1 plus delta. Okay? So just subtract 1 from everything, from both sides. Negative 1/3 minus 1 is negative 4/3. So delta is negative 4/3 plus the square root of 70 over 6. That's the exactly the largest delta that we can possibly use so that the conditions in the definition of the limit are satisfied. And to see that this agrees with what we did before, notice I did negative 4/3 plus the square root of 70 over 6, and sure enough I got the same value I did earlier for delta. And of course, if I do negative 1/3 plus the square root of 70 over 6 right here, just to find the x value, 1.0611, so forth, that was exactly the value we found for the x plus negative, let's see, what was it? It was 1 plus delta. Okay? So that gives you an example that we can look at, an example of a kind of problem we might have where it's not linear, where it's quadratic. Next video we'll talk about formally looking at one-sided limits.